Much for having me here at KITP. Today I will talk to you about ground states of local Hamiltonians. I am a computer scientist, and so for me a ground state is just the lowest energy state of a local Hamiltonian, and I will only be thinking about local Hamiltonians that are fixed. There's no time dependence. It's very just simple. It's like linear algebra, computing lowest eigenvectors of matrices. What I'll talk to you about is work that was done mostly 2-3 years ago, and so this talk is more going to be me asking questions about what we should try to solve next and places where I'm stuck and I'm looking for help. So, please, if you have ideas, please let me know. Okay. Does this work? It's off. Here we go. Okay. So the motivating question is the following. What makes a ground state hard to synthesize? So say tomorrow, someone comes about and they've built the quantum computer of your dreams. It can do whatever you want, however big a system you want to simulate. It's got the capability. How do you go about synthesizing the ground state of a local Hamiltonian? These objects are physically interesting. You want to be able to simulate them, synthesize them so that you can maybe measure them, evolve them, do whatever you like with them. But how do you go about synthesizing? It's not clear. In that effect, can you prove that it's hard to synthesize the state? Can you show that if you were able to generally synthesize ground states, the algorithmic power you would have would be significant? Maybe you accept that it's hard to synthesize states, but you come across the following kind of amusing question, which is, maybe if I have one copy of the state, it's significantly easier to synthesize two, right? There's nothing really precluding that. After all, you already have one copy. You've sort of found one state. Is it any easier to synthesize the second copy than it is to synthesize the first? All these questions sort of live in a space which is a nascent kind of complexity theory, which we call the complexity theory of quantum states. And let me say one or two things about how it connects to the traditional paradigm of complexity theory. So there's a playing field which is really borrowed from classical complexity theory, which is that we can frame computation in terms of inputs and outputs, classical inputs, classical outputs. You take in some sequence of binary, sequence of bits, you output a sequence of bits, classical in, classical out. And in this regard, you can frame a bunch of complexity classes. In the talks today, you've heard about classes like BQP, QAC0. I'm going to say a little bit about QMA. These are all classes which take in a classical input and also return a classical output, but in the interim, go through some sort of quantum computation. Classical into classical out, but they go through quantum computation in the middle. But what I would like to talk to you more about is these questions of state synthesis, which is we're interested in problems with the classical input. For the most part, I'm going to be thinking of the classical input as the classical description of a local Hamiltonian system, and a quantum output, which for the most part is going to be the ground state of said system. Okay, so what's known? Well, computing the ground energy, the trace of the ground state with respect to the Hamiltonian, that number, computing that number to some suitable precision, that's QMA complete, where QMA stands for quantum Merlin-Arthur, but it's the quantum analog of the complexity class NP, and it subsumes that class. So what this means immediately is that computing just the ground energy for a generic Hamiltonian system should be hard. It should be so hard that if you could do it, you could solve any NP problem that you'd like. And this poses a significant problem for generating psi. Because if you could generate psi, we actually know of a very simple algorithm, it's called phase estimation, that takes the state psi and comes up with a really, really accurate estimate of its ground energy. So that tells you that because computing the ground energy is hard, computing the state is also hard. And okay, thank you for your time. No, there's more to this story. All this tells us is there's no efficient algorithm for outputting psi from input h. But it yields some very good questions that should be answered next. The first is that, okay, in the face of absolute hardness, is there an approximate solution? Can you generate some state which is pretty close, is maybe not the ground state, but something similar? Is that doable? This is most commonly known as the quantum PCB conjecture. It's one of my favorite conjectures out there. A second question is, let's be a little bit pedantic about the actual complexity of generating the state psi. Is it really that much harder than computing the ground energy? Could we actually compute the state if we knew how to compute ground energies? Like, say tomorrow someone proved that QMA was equal to P, that you could compute ground energies efficiently. Would that immediately, give us an algorithm for computing ground states? That's not clear. And this question is sometimes known as search QMA versus decision QMA. And the last one is the one I mentioned on the first slide, which is now given one copy of the state, maybe it's easy to produce 2 copies of the state, then 3 copies, and so forth. And all the hardness of generating the state is embedded in that first copy. Once you get the first copy, you can just Xerox it as many times as you like. Really, the hardness was embedded in the first thing. That's sort of the state of the affairs for classical problems like NP. So during the rest of this talk, I'm sort of going to go through some results in this space. Please let me know if you have any questions, and happy to answer. I would prefer interaction. Okay, so let's talk about approximate solutions to constructing ground states. So the first reasonable approach that you might have is, okay, instead of getting the true ground state psi, what if I got some state which had overlap with psi? It was close in trace distance, had some good angle. Well, unfortunately, you can actually show that even finding a state which has an angle which is 1 over polynomial should be very, very hard. And that's because if you had such a state psi tilde, you can take a combination of the Grover search algorithm and phase estimation and actually amplify that all the way to actually having the state psi. So it says that constructing up to like polynomial factors, constructing any approximation, anything that has good angle with the ground state, is just about as hard up to the polynomials. Conversely, you can look at this a little bit optimistically, which is to say that ground state preparation is significantly easier if you have a warm start. If you were able to come up with some sort of state, some ansatz, I think I'm using that word correctly, that has good overlap, then ground states are easy. You don't need to worry about anything. There's an algorithm, so you're good to go. So what this tells you is that maybe the more interesting notion from a complexity theoretic standpoint, by the way, if I ever say something like most interesting, that's an opinion piece. I'm not going to... So the more interesting notion to me is approximating low energy states. So what's a low energy state? A low energy state is any state rho such that the energy of rho is really the ideal ground energy, this lambda minimum, plus some epsilon perturbation in the overall norm of the Hamiltonian. And so a nice question is, how hard is it to construct low energy states of local Hamiltonians? This question is slightly different than how hard is it to estimate the energy. I'm asking how hard is it to construct low energy states. Okay. So unfortunately, there's an open conjecture, probably one of the biggest conjectures in quantum complexity theory, called the quantum PCP conjecture, probabilistically checkable proofs. And it states that, actually constructing even those low energy states is just as hard. Is also QMA hard. It's no easier to approximate than it is to solve exactly. And so therefore it follows that it should be QMA hard to even construct approximations of rho. Yeah, question? Yes. Epsilon to be, oh yeah, do you mean huge or small? Yes. First, under some threshold, approximation becomes hard for some constant threshold. Think of it maybe like 1%. The rationale is that the classical analog of this, it's hard to approximate like 3-sat formulas to something like 12.5%. So there's some universal constant below which independent of the Hamiltonian, after which approximation just is futile. It could be. I mean, we don't know. Because unfortunately, it's a conjecture. In fact, what actually happens is, there are proposals people have put out for families of things which kind of may look like this, and then you just show that for any energy epsilon, it's actually easy to approximate to that for any epsilon. And your algorithm's runtime can scale with the approximation factor. Yeah. Any other questions? And because of the classical PCP conjecture, because local Hamiltonians are just quantum generalizations of SAT formulas, we actually know that it's NP hard to even construct approximations of rho. Just classical Hamiltonians is hard to construct ground states or even approximate states for these guys. But this, again, leaves open a more fine-grained question as to the level of intractability. In particular, these questions of these fine-grained notions of intractability have significance to notions of entanglement complexity. And to understand these statements, to understand, what this kind of granularity is, we need to understand a sort of a notion of what I call description complexity. The way I like to describe it is that there's some sort of fundamental relationship between description length and entanglement structure. So when I say description length, I sort of mean that, say someone comes up to you and says, I would like you to prepare this quantum state. They will provide you with some sort of explanation of how to prepare that state, some description of which state they'd like prepared. Maybe they tell you a circuit that prepares the state. Maybe they tell you an MPS. Maybe they tell you a PEPS, right? Some way of describing that particular state that they want constructed. And if you explain quantum entanglement to someone, the easiest way to say it is that it doesn't really suffice to describe each individual particle. And the sort of natural corollary here is that the longer the description of a particular state, the more complex the underlying entanglement is. And so we can think of description length as some proxy for sort of the entanglement complexity underlying a state. Yes? Mm-hmm. Yeah. No, that's a perfect question. And you spoiled my punchline. I don't know, it's all good. Yeah, so what if you just said, hey, look, here's the Hamiltonian. The ground state I want is the minimum eigenvector of this matrix. That's a description. And the computer scientist would go, that's a perfectly valid description, except it is a useless description to a computationally bounded person. So sort of the notion of a description has to be taken always in context as to who is reading the description, right? You can explain the law by giving a textbook to a child, but that's useless because they can't really understand all the nuances. You have to explain it at the level of the device. So when we talk about description complexity, we have to describe the state in a way that our bounded polynomial time quantum computer could understand. So unfortunately, describing the state in terms of the Hamiltonian, while a perfectly pinpoint accurate description of the state, is not a description that is at all helpful to a bounded polynomial time computer. And so therein lies this sort of intricacy, that really when we talk about description complexity, we're sort of talking about maybe a correct notion of like efficiently verifiable description complexity, but writing that down every time would sort of be a mouthful. Yeah. But fantastic question. Yes, please. Yes. Mm-hmm. Yeah.
So
Indeed.
I would say that's basically the same thing on the right hand side, but the left hand side apparently is very different.
Okay. So there's a subtlety there with the Torah code, or any code in general, which is how you measure description complexity. If you allow yourself notions of alternation between classical and quantum circuits, the states may have small description complexity. But if you say restrict yourself to constructing the Torah code using fully quantum computation, so you take whatever classical computation you wanted and you consider it as part of it, you actually can guarantee that to construct a Torah code ground state, the minimum depth has to be log n. It's a provable lower bound. I'll actually show a sketch of such proof in a bit. So yeah, it's not, I don't mean to use this as an exact science in any means. It's really a proxy. Yes, please.
What relationship between description length in this language and circuit complexity?
Okay, so circuit complexity of a state is one way to describe a state. It is certainly not complete, right? There are other ways to describe states outside of a circuit that constructs them. So a good proxy for description complexity might be to talk about circuit depth or circuit size, but by no means is that complete, right? There are other techniques for solving problems that circumvents circuit complexity. Okay. All right. Okay. So what actually follows is that in addition to being hard to construct ground states, in fact, turns out that it should be hard to describe ground states. So while we have simple descriptions such as, circuits, maybe like a brickwork circuit or an MPS for describing ground states, in general, we believe that these descriptions should be insignificant. And that's because there are some classically describable quantum states that are so simple that if you gave me the classical description of this state, I could just verify all the properties I want about this state entirely classically. Like there's no quantum computation necessary to verify that, whatever state you've described to me truly is the ground state of a Hamiltonian. Therefore, if you believe something like a complexity separation, like QMA does not equal NP, that the power of the quantum analog of NP is strictly more powerful than the classical, it follows that there must be some lower bound as to the description complexity of ground states. So this is something we kind of believe, but was something we don't know exactly how to formally prove. We have some evidences moving us towards this direction, but as complexity theorists, this is sort of a nice big goal, something I'm happy to spend the rest of my career thinking about. Okay. So going back to the question just asked a second ago, one proxy for description complexity might be circuit depth, and it's a great first step to think about. It gives you sort of a nice yardstick for understanding the complexity of states. So here I'm going to think about a quantum circuit where the connectivity between rows is all to all. So any gate can talk to any gate in the following row. There's no restrictions there. What follows is that if you can describe a state using a log n depth circuit, then we might call this trivial because it follows that there is an efficient classical algorithm, an algorithm that runs in polynomial in n, this parameter, for calculating the energy of the state with respect to any local Hamiltonian. If you go a little further, if you go up to polynomial depth, This sort of becomes the regime of tractable quantum states, in that if you could construct a state if you could describe a state using such a circuit, then there is an efficient quantum algorithm for calculating the state and verifying properties about it, but it doesn't seem like we know how to at least black box solve it classically. And going even further, you enter the regime of intractable quantum, which is that these states exist, there is a circuit to describe them, but in polynomial time, we wouldn't be able to verify some property of them. Unfortunately, most states sit in this bad regime. The bottom two regimes sort of describe the corner of states where, we can at least kind of work and do research in. Okay. So there's a nice statement, a conjecture that was asked in 2014 by Friedman and Hastings that said, is it the case that there are n-qubit Hamiltonians such that all the states of energy less than epsilon n require omega of log n circuit depth? Meaning that all those states fall outside that classically tractable regime and fall into that yellow quantumly tractable regime, at least. At least there's no very simple naive algorithm for this. And there was a bunch of work on this, some of it by myself, and we resolved this theorem about 2.5 years ago by constructing actually a local Hamiltonian system which has the property that every state of energy less than epsilon n requires at least omega of log n circuit depth. And for this question, I can answer you that question, and it is something like 10 to the negative 24, I think the epsilon. It's not a realistic thing, but it's very tunable. If you don't blame me, you should blame whatever error-correcting code theorists, because as they improve their error-correcting code parameters, it naturally will improve. So you can blame anyone working on error correction for but not me, okay. So I'm going to say a little bit about how we prove this theorem, and then I'll go on to some sort of interesting open questions around this space. Okay, maybe to contextualize and kind of go through a recap again, let's start with the classical PCP theorem, which is a very simple idea that you have a verifier who's got some, say, 3-step formula. He sends it to a prover. The prover sends him an assignment back showing that the formula is satisfiable. And a verifier would necessarily need to read the entire proof to check the correctness until you actually apply a PCP theorem. So the PCP theorem says there's actually a special formula, a special subset of proofs which are complete, meaning you can always write a formula as an equivalent formula from this family, so that now, once you take the assignment, you only need to read a constant number of bits to be confident to say 99% confidence. That checking that proof is very, very easy. Or another way to say this in terms of approximability is that it suffices to just estimate the satisfiability of the SAT formula to some 1% multiplicative error. That you didn't actually need to read everything, you just need to estimate the energy or the satisfiability to 1% multiplicative. The quantum analog of this statement is similar, except now you ask about a Hamiltonian, and a prover provides you a ground state. And the quantum analog, or the quantum PCP conjecture, is that it's QMA complete to estimate the ground energy up to this 1% multiplicative error. I'm using 1% here instead of epsilon just because it somehow seems a little simpler to write down. But it could be, maybe it's 0.1%, maybe it's 100th. We're sort of open to that. This NLTS theorem is just the direct consequence of this quantum PCP conjecture, assuming QMA does not equal NP. It follows because if you could classically describe all of these some low energy state below 1% using a low depth circuit, then it would just, in conjunction with this, would imply that QMA equals NP, because you wouldn't have to send me the quantum witness anymore, you could just send me the classical witness. So, interestingly enough, a major statement in quantum complexity theory has actually implications to the description complexity of states And moreover, using this assumption I said that description complexity is some sort of proxy for entanglement, is a statement about the entanglement complexity of ground states. So this is one of my favorite parts about this whole research avenue, is because it lets you say that computational tools are sort of a toolbox for describing entanglement complexity. When someone says that entanglement is complex, previously was a little vague, but the nascent introduction of circuit complexity really gives you the machinery necessary to make those statements rigorous. And the way you make such statements rigorous is you use ideas such as description complexity to quantify these sort of nebulous notions. Okay, so maybe it's time to give some sort of proof sketch of this NLTS result. And I should say, and why this talk connects to this overarching workshop theme of error correction, is that currently the only known constructions are Hamiltonians that derive from quantum error correcting codes. It's a very open question as to whether there are other constructions that are either, fundamentally devoid of error correction or give us new insight into error correction in its very nature. And that's something that, I highly recommend thinking about. So why codes? Well, codes are, by their very definition, a really good construction of robust entanglement to noise. Right? They're designed, their very nature is designed to correct errors that appear on single qubits. Like, you apply some depolarizing noise channel, and nevertheless, the fundamental information is still there. Right? So you couldn't have really destroyed that much entanglement. The complexity must still arise, even if you apply errors. What isn't so clear is while they are designed to be robust to local noise, it's not a priori clear why that would provide robustness for all the low energy states. Because you can be a low energy state without being defined by taking a zero energy state and applying a local perturbation. Because one thing you could do is take a zero energy state and shift it like in the Bloch sphere by a small angle. That's not a local perturbation at all. It's not centralized to a certain set of qubits, but nevertheless, it's still only a low energy perturbation. So it's sort of incredible that codes, while constructed to be robust only to local noise, also have this external property of providing robustness to a more general notion of approximation. Not all codes. But every code has some regime, which you can define. If you want to be robust to constant, you have to take very specific families of codes. But for every code family, you can define what that regime is. For most codes, it's like 1 over n. Yeah. Okay. So in order to prove this NLTS result, we need a way of proving circuit depth lower bounds, quantum circuit depth lower bounds. Because, after all, we're talking about quantum circuit descriptions. So somehow I need a machinery to do this. And here's where we start. We start off with this fact, which is that if you ever give me a T-depth circuit C, then the local Hamiltonian defined by taking the projector onto the Tth qubit being a 1, and then conjugating that by the circuit C, this Hamiltonian has two properties. One, it's 2 to the T local, and second, it has a unique ground state, which is C applied to the 0 state with spectral gap 1. Let's do the proof of all the parts. The 2 to the T locality you can show by induction on the depth of C. You can show that, each Hamiltonian, as I evolve it under one more depth of the unitary C, I'll get this 2 to the T property. The uniqueness of ground state is not too hard to see. If you conjugated the Hamiltonian by the inverse of C, you'd see that the remaining Hamiltonian is just the one which, projects each qubit onto 1. That Hamiltonian is easy to analyze. It only has one ground state, which is the all zero vector, and its spectral gap is 1. Because you're conjugating by a unitary, spectrums don't change of matrices, so it satisfies. Yeah? Oh, sorry. The summation should be over t. I'm sorry. Yeah, it should be the tth Hamiltonian. Apologies. Yeah, there's one term per qubit. Yeah. Oh, no, sorry. It should be 1 on I. That's right. That should be I. Yeah. Okay. Yeah, that's the typo. Okay. All right, let's prove another fact. Let's say you have a set of strings x1 through xm, and they're points so that the distance between them is some number at least L. So meaning that they're points in the Boolean hypercube, and the distance between them by, at a distance is at least L. It follows that any state psi, which you can write down as a linear combination of these basis vectors, cannot be the unique ground state of a local Hamiltonian. The key word here is unique. That it cannot be the unique ground state of a local Hamiltonian. How am I going to prove this? Well, I'm just going to show that if it is the ground state, I can construct a second state disproving uniqueness. Easiest way to disprove any statement about uniqueness is just show there are two. So here's what I'll do. I'll define psi prime to be a vector that's necessarily different, because I'm just going to flip the first coordinate, the first non-zero coordinate, but let's just say that's alpha 1. And now, for any L local term, I'll see the following. If I compute the energy of that local term with respect to the original state psi, I'll get out this alpha j prime, alpha j, sorry, there's a little j prime there, it's hard to see, xj prime, h xj. But now, let's look at this coefficient here, this xj prime, h xj term. I claim this term is 0 unless j equals j prime. Why is that the case? Well, it's because I'm going to consider an L local term for h, meaning that Hamiltonian term could at most, when you act on the state xj, could at most flip L of the bits. But since I assume that the strings are kind of far apart in this space, it follows that all of those terms will be 0 when j, j prime are not equal. So what follows is that the only remaining terms are the diagonal terms. And now notice that I just get alpha j squared. Any sign information attached to the alpha j is lost, meaning that psi prime here with the negative signs here has the exact same energy. So then what I get is for any local term, the energy of psi with respect to h is the same as that of psi prime. So if I add up a bunch of those local terms, linearity, does the rest of the work for me, and I get that we have non-uniqueness. Okay. Corollary. It follows that this is a great way of proving a nice circuit depth lower bound. Why is that the case? We have to use the two theorems from the previous pages. So one was that if you had the states, you would be the unique ground state. And the second one was that if you were the output of a low depth circuit, then you are a unique state. So the contradiction of both being a unique state and not being a unique state is enough to prove your circuit depth lower bound. So it tells you that any states that's supported on this set of strings which are far apart cannot be the output of a low depth quantum circuit. Pictorially, the way I like to think about this is I think of my set of points as just a bunch of points on the Boolean hypercube that are all kind of far apart. They're at least L apart, and I can prove this log n lower bound. I can lift this corollary a little bit to instead of just being about specific points, I can consider subsets of points. As long as the distance between the subsets is far, I also get the same log L depth circuit lower bound. It's the same proof. You just have to do a few more steps. I call these kind of distributions well spread. So if I ever have a well spread distribution, it tells me that any state supported on that well spread distribution, whose support is at least on two of the regions, cannot be generated by a low depth circuit. You can make this statement robust using some nice techniques of Chebyshev polynomials that I won't get into. And you just do the following. You say if you have any two subsets, S1, S2, whose distance is at least L, then any distribution D with mass with mass at least mu on both halves has to have circuit depth lower bound of this. And as I write this, I realize that I have a typo here. There is a square root of n here, which is very, very important. I'm so sorry. It's L squared mu. Oh no, I put the square. Okay, we're good. Never mind. As long as you have the square and the L squared, it's all okay. Okay, never mind. I was right last night. Phew. Okay. So, you know, in particular, if you have the distance between any two sets is n, you get log of n squared mu over n. So as long as mu is a constant, you get like a log n depth lower bound for such a state. So any state which yields a distribution. So if you measure the state and you get out a distribution which has this well spread property, you're good to go. Okay, so I thought, you know, you might say, Chinmay, I thought you were going to talk about error correction. Okay, here we go. Let's find some well spread distributions. Where do they occur naturally? And to see that, there's a really nice visual associated with classical error correcting codes, and it's the exact same picture. Classical error correcting codes are just, you know, they're the image of a linear space with the property that this distance between image points, the Hamming distance, is far. A really good code is one where that distance is like scales like order n. And this is the view of the exact solutions to a linear distance error correcting code. But what does the low energy space look like? For classical codes, it should be any vector that is supported on the approximate solutions to the error checks, so things that satisfy 99% of the checks of the error correcting code. And in particular, if whatever matrix H that describes the error correcting code has a property that we call small set expansion, the picture should look like this. In particular, there will be these little balls of radius about epsilon n that will propagate from the solutions. Anything close enough to a solution is an approximate solution. But in addition, there are these other kind of phantom clusters that form of solutions that are very far apart. The nice property, though, is that if you have the small set expansion, necessarily the distance between any two of these clusters has to scale linearly with n. So the property of being an error correcting code with distance n and small set expansion is that the low energy space looks like this. Okay, so now we're really cooking, because what do we have? We have a well spread distribution, right? Any way you cut this distribution up into some of the clusters on one side, some of the clusters on others, will certainly have the distance between the two sides scales linearly in n. So we're primed to apply our circuit depth lower bound techniques. There's only one catch, which is that if you have a low energy state psi, which was only supported on these purple regions, then there exists another state phi of the same energy, but only supported on one purple region. How do you prove this? Well, it's a very similar proof to how we did previously. You say, look, take whatever state psi you had, which was supported on with each Vj supported on a bunch of these regions, flip with the first one, and do your calculations, and you'll get a second state of equal energy, who is now psi minus psi prime. So then you can actually extract out a low energy state that's exactly supported on one of the regions by just taking their difference. So this is kind of frustrating. In the very attempt to try to prove that any state supported only on the purple regions, a low energy state has high circuit depth, you inadvertently create a second state which has low circuit depth because it's only supported on one of those regions. So, you have to do something else, right? And the resolution to doing something else is we have to start thinking about not just classical error correction, but quantum error correction. So this is what I just said. So to do that, we're going to use some nice uncertainty lemma. So the nice thing about quantum error correction is that it sort of sits in two bases. There's like a two basis thesis going on. And the really nice thing is that we have this nice uncertainty statement in quantum mechanics. And basically, one way to phrase it, there's multiple uncertainty lemmas, but one way to phrase it is that if you have a state that is almost entirely supported on a really small region S in one basis, in any anti-commuting basis, it has to be supported in a very large region. Like, you couldn't have concentrated the mass on two small regions in two anti-commuting bases. So what follows is, instead of trying to show that low energy states of classical codes are well spread, that proof technique will end up being futile, is we'll instead talk about low energy states of quantum error correcting codes. And instead, what we argue is that the low energy state in at least one of the two bases, in at least the X or the Z basis, must be well spread, and therefore a proof of circuit depth lower bound. The intuition you should have is that, look, if you have an error correcting code like a toric code, and you look at all the possible measurements of the toric code, you take your toric code and you measure all the qubits. You're going to get one of four types of measurements. You'll get out loops which are trivial topologically. You'll get loops that go one way, loops that go the other way, or loops that go the both ways. You have to fall into one of these four categories, and the distance between these categories scales like the distance to the code. In the case of the toric code, it's root n. But this picture exists not just in one basis, but in both bases. And what follows is that if you measure the ground state of the toric code in one basis, say the Z basis, you'll get one of the four measurement classes. You have to fall into one of these. But then if you did the same measurement in the other basis, then it won't be concentrated. It'll be spread out over those regions. So what you do is you take a good error correcting code. You take an error correcting code which has good quantum distance and good quantum rate. The good rate was necessary for our proof in order to prove well spreadness. There was a follow-up work by Kaufman and Louis Golovich actually showing that good rate is not necessary to actually get this kind of well spread intuition in at least one of the two bases. And that gives you your circuit depth lower bound. And this is needed for the shape of the distribution. Okay, well, what does NLTS prove and what does it not prove? NLTS does not prove a circuit depth lower bound for all the low energy states of an error correcting code of a Hamiltonian. It does prove a circuit depth lower bound for all the low energy states of a Hamiltonian. It does prove that some Hamiltonians cannot be approximated by low depth states. But crucially, it does not prove the quantum p-speed conjecture. And this is because it's still possible that there's a different way of classically representing states so that approximating Hamiltonian ground energy is in NP. For example, all the states we showed this NLTS property for were all code states. We don't know if a family that has NLTS that doesn't look like a code. And all the codes can be simply represented using the stabilizer formalism, if you're familiar with that. And as a consequence, it means that there is a different way of classically representing states. So this yields some really nice questions. If I had more time, I would talk to you about some of these. I'm only going to talk to you about idea one today. So one idea is to try to prove stronger circuit depth lower bounds. One of my favorite results in this area is that we should be able to prove even stronger circuit lower bounds. And one example is something Henry discussed this morning called the magic hierarchy. Magic hierarchy, the first level of which I've drawn here, which is you start off with a state, you apply a Clifford circuit, and then any constant depth quantum circuit. And first level states are also easy classical descriptions of quantum states, meaning that any state describable in this first level can be verified on a classical computer. Natalie Parham constructs Hamiltonians for which the exact ground states are not first level states. A really exciting question in my mind is can you improve this statement to low energy states? And in the interest of that, I'll leave this as my only open question for now. Come talk to me about others if you're interested. Okay, thank you.
Any more questions?
Yes, please.
Do you have examples of states with short description complexities that don't have short circuit depth?
Short description complexity, but don't have short circuit depth that's verifiable.
Yeah, like whatever your definition of short description complexity is. Like,
Yeah.
you're saying that it goes one way, there's a short circuit that implies a short description. That like was something that.
Yeah, I think the canonical example is any Clifford circuit, right? That's a great example of something where you can have a circuit whose depth goes out all the way up to n squared, but you would classically do all the simulation for it. Even better is like you can take a Clifford circuit and you can sprinkle in a few non-Clifford gates, right? These kind of situations, there's studies of like parameterized complexity of these models, and these are all great techniques. Yeah, in fact, if you sprinkle in the non-Clifford gates, you can get much, much taller. You can get to like n squared log n, and it's still classically verifiable. Right, so, yes?
So what you said earlier about all states for which we like have this LTS, I guess all Hamiltonians, being codes. I guess now we have like proofs of stability of these like code Hamiltonians to small deformations. So like, does that say anything about like having LTS Hamiltonians which are not codes, but are only like close to being codes?
Yeah, correct me if I'm wrong, but the deformations are to the states, not to the Hamiltonian, right? Like the Hamiltonian is morally the same.
The Hamiltonian is comparative, and the proof is that the ground state subspace is a quasi-local unitary.
Yeah, I guess, okay, if you take a Hamiltonian H and you add to it another Hamiltonian, which is a minor perturbation, then the energy of a state in one Hamiltonian cannot deviate too far from the energy in the other Hamiltonian, right? So since low energy states are just defined as energy less than or equal to epsilon n, if the perturbation between the two Hamiltonians was, say, of size epsilon to the 10, then by just adjusting your parameter, you would just, the proof would port over. So I guess maybe you should say that, when you prove that a particular Hamiltonian has this property, you've actually proven it for all the Hamiltonians in a small ball around it, right? These are all kind of very robust notions.
So you don't regard like these like small perturbations to codes being like different from codes?
Not in this robust sense. I mean, like the real big steps needed are that we talk about combinations of codes and computation, or something ideally that doesn't look like a code, but one can prove such an NLTS property. And then that might suggest that it does have code-like behavior that we didn't a priori expect. Right? So.